Hello. Hello.
Yes, sir.
Okay, so I see that some of you have joined. Not many. And these 5 minutes have passed. So let me quickly take a poll to see what's going on here. Can you just fill this poll so that I have some idea about what's going on? Okay. So that's the beautiful number. And the CRS people are not coming. Okay, I will keep that in mind.
So before I forget,
Uh,
EPSOT lecture that you have shared is not available.
Sorry,
The video for the EPSOT
which lecture?
EPSOT lecture, the last lecture.
Oh, that is not available.
No,
That's not
it
uploaded
says
properly.
video.
Then?
Yeah. Video is no longer there.
Oh, okay. I will just check it out. What's going on?
And sir, I told regarding this in the last class that the slides that you are using is not like I cannot find them yet. Mostly.
Which slides are you talking about? I have only one slide. Hello.
Okay, yes, that has been uploaded. So it was I could not find it 2-3 days ago. So yeah, it is uploaded now. Sorry.
I mean, this has been uploaded since the last time you told. Actually, I think the very day when you told, I had uploaded.
Okay. So I had some issues, I think.
Yeah.
Hello, sir.
Yeah.
Sir,
Yeah. Go ahead.
I have one question that as you have mentioned two terms while you were teaching the randomized version of Quicksort, that one is expected runtime and another is average case runtime, and you showed us that those two things are
Right.
exactly same thing. So in general case, my question is, what is the
For
difference?
that, those two things,
approach
no,
of the
that
two
is not
things?
true. That's not the same thing. Yes, that is not the same thing. That is two things are same for the case of
Quicksort.
for Quicksort.
Okay. So in general, these two are not
Okay.
same.
For general, these two are not same.
Okay.
No, not at all.
Okay.
Okay, because in general, these two are basically saying that so the expected thing is that algorithm is going to make its own, will basically be tossing its own coin, right? It will
Yes.
use its own randomness, and probability of giving a correct answer, or probability or expected runtime is like over the probability of its coins tosses, what is the expected runtime. Okay, and the average case is that when the algorithm is not randomized, algorithm is deterministic, but the inputs are coming is drawn from a distribution.
Okay.
Maybe from the set of all possible inputs, one is drawn uniformly at random. It doesn't have to be uniformly. Sometimes it is drawn according to some other distribution also. Okay.
Okay.
In that case, what is the runtime is the average case runtime. So average case is for a deterministic algorithm. Expected is for a randomized algorithm. Okay. It so happens that for the quicksort, these two terms are same.
Okay, sir.
Any other questions? Yeah, so I had told you guys that said that we will be putting up an assignment on Friday or something like that. That has not been done yet, but it will be done today. So so the first assignment on which will be on sorting will be uploaded today, maybe right after the class. Okay, and yeah. Okay, so today, okay, let me share my screen. Can you see my screen?
Yes, sir.
Hello. Okay. Okay. So today will be kind of the last. I mean, not the last actually, but somewhat slightly different from what we have been doing so far. So so till now, what we have been doing is what we told in the last class as comparison sorts. Comparison sorts meaning you have been guaranteed that there are some particular so that this set is coming from a totally ordered set. That's it. We don't know anything about whether the elements that are coming out are numbers or real numbers or rational numbers or sets with some kind of a ordering between them, or whether they are some other concepts, maybe points in higher dimensional space and so on. We have no idea. All we know is that they has to have a totally ordered set. It's coming from totally ordered set. And with that knowledge, we had designed algorithms, right? We had designed algorithms like this insertion sort, bubble sort, selection sort, and then we moved on to merge sort, then quick sort, then heap sort, and we all of them we kind of gave some various algorithms, better upper bounds, as good upper bounds as you can get, right? So we had things like order n square initially, and then we somewhere in the merge sort we hit n log n with some extra space. With heap sort we also hit n log n, and so on. This is the upper bound results. At the same time, we had this lower bound result that we saw I think a couple of classes back, that any such comparison sort algorithms will take omega n log n number of samples, comparisons, right? At least this display number of comparisons. Now this is all fine, but what about in the real life when, say, sometimes we know that the things that we are sorting, they are not just some random numbers or something arbitrary numbers, but they have they come from a much smaller set. So for example, if the inputs are words, English words, okay, something like a dictionary, and we want to sort them in dictionary ordering, or what is also known as the lexicographic ordering. So Okay, so here we know that this kind of things, they have lot of structure in them. What is the structure? That a word, say something like a word cat, has 3 parts. Now each of the part we know can be at most one of 26 different letters. So any string, any letter is basically, any word is basically, say, if I write bread, it's 5. So some integer number of word alphabets, each of them can be at most 26. Right? So, and this 26 thing also we know, right? So if I just look at the last letter, the first or whatever you think of, if I look at any of the letter, so they can be only A to Z, right? I know that already. In that case, this is not an arbitrary collection of what are things from which it is coming. It's not an arbitrary total order. This is input has way structure than just an arbitrary input. In such a, can we make use of some cleverer algorithm? So maybe let me ask you simple, okay? If I give you a, say, a single letter, okay? I give you a string, I mean, say 1 letter word for the sake of it. Okay, just 1 second. Yeah, so say I have a set of alphabets. So each of these words is Z, A, B, D, Z, A, C, something like that. And if I ask you to sort them, how will you do it? If I ask you to sort this set of all, this set of how many? 1, 2, 3, 4, 5, 6, 7, 8. So let's say 8 different 8 words of one letter each. How will you sort them?
Look at the corresponding position of the alphabet in the I mean one, like A is 1, Z 26, and then sort the numbers.
Then sort the numbers. What do we mean? Okay, so that is one way, right? You can say that, okay, you will now go and say that, okay, I will write for each of them, I will have some numbers and you will sort them, right? Say 1, 1, 2, 4, 26, 1, 3, and so on. So in that case, if the input is what is it, n different alphabets, what is the time to sort them? How much time to sort them? How much time will your algorithm take?
Order of n log n.
Order of n log n, by just replacing all of them into this kind of things, right? And by numbers and then doing it. Okay, so you are giving me an order of n log n algorithm, but I say that you can do better. Can you guys maybe just take a time for a couple of minutes? Everybody think. What will you do? Don't try to just recollect from your what you have learned in your school or college or whatever stuff. Just try to be innovative and just think. What will you do? you have been given a string of n different alphabets, right? And you have to produce me a string of n different alphabets, which is basically the same string sorted. How will you do it? N login, you can surely do it. I can see. Can you do better?
Sir, we can just count the distinct characters and then sort them by their alphabetical order. We don't even need to sort.
Oh, very nice. So what you can do, how can you count them? How much time will it take to count them?
Sir, it will take ON.
Okay, so let's say I want to see how many A's are there. I will make one pass over the whole thing and count the number of A's that are there. Number of A's that is there is here, in this case 3. Now how many B's that are there? I will again go over the whole string and count the number of B's that is there is 1. Similarly, how many C's that is there? I will go over the whole string 1, D 1, say something like E 0, and I keep on going like this till I have Z, okay, 2. Now by doing so, how much time did I take?
Sir, in K time, if we are
Each of
counting,
this,
yeah.
right? It's ordered
Is
n for
there
each of them, right?
K alphabet, then it would take total of ON K time.
Yeah. In this case, we know 26 alphabets, right? So the total number of
Sir.
time that is taken is 26n, right? Yeah. Somebody was asking something. Hello. Hello. Was there somebody asking something? Am I audible?
Yes,
Yes,
sir, you were
yes,
audible, you were
sir. Yes,
audible.
sir.
Okay. And once you have got some set like this, or this whole set like this, then can you produce me the whole string again? Of course, because I know that these are counted, right? 3 A's. So A, B, C, D, and none of them is 0, then Z, Z. Is this a sorting of this? Of course it is. What is the time taken? It is 26n, which is order of n. So if I am guaranteed that all of them are just letters from the English alphabet, since I know the number of letters is just a constant, so 26, I can now sort it by doing this kind of counting trick. And I'm managing to produce a algorithm which is better than what any comparison based algorithm can do. Now you can say
But you're
why
doing this
or
at a
how. Yeah.
high cost of space. Like you're doing it at a very high cost of space, right?
You are doing it at not that much of high cost of it. Tell me, what is the space cost that we are taking?
You're
The
managing
space complexity so should be constant,
26
right? Because where we
signs
store like
array and keeping
Yes, so
track
there are
of them.
26 of
26.
them, and
26.
each of them I have to just track the number, which is log n, right? To store a number which is at most n, all I need is log n bits. So total space is 26 log n. Is this clear?
Yes, sir.
So
But the
26.
same trick,
Yeah.
for large, if you were to say, let's say, do integers up to large some number,
Right,
then
of
it'll
course.
start getting bad.
Then it will go bad, right?
Yeah.
So I have used crucially the fact is 26. is a constant. It's a small constant, right?
Sir, I
That we
just
have
missed
used.
where the log n space complexity.
Okay, so for beside A, what do I have to store? What is it that I have to store?
Number of occurrence and integer.
Number of A, right?
Yes,
That's
yes.
what we have to store, right? Number of A's. So number of A's. So how much that can be at most? Can be at most be n,
Yes, yes.
right? Any number between 0 and n. To store a number up to n, how many bits do I need to use,
Okay, okay, log n, yes. Okay.
right?
Yes, sir.
So the total number of space is basically some order log n. Okay. Now I have kind of, so I mean, you tell that, okay, but the order log n is extra. Now, if you go back and look at any algorithm that we have used, okay, say it be the, any of these above algorithms, okay, I have not told, I've talked about the extra space of order n and all of them use the space of order log n. That much was required. Can you guys think and tell me why did this order log n space, where was it necessary? Say in the insertion sort or merge sort or quick sort or heap sort, any of them? So I claim that all the algorithms that we have seen till now, order log n space was used.
The temporary variables which were storing the numbers.
Temporary variables which are storing the numbers. Which numbers?
So in case of
Which
insertion,
numbers?
in place insertion sort, we were keeping track of the individual number which must be shifted.
Okay, so that is one place you can think of, but you're right. I mean, there's something else also we were storing, which we almost assume that we don't need it at all, but we need it, which is that we had the indexes, right? For I equals to 1 to n. When we write a while loop or for loop, we had the I equals to 1 to n. We have used it, right? All of the places.
Yes, sir.
How do you store I? How many bits do
Sir,
you need to
in
store that I?
binary, log n digits, log n bits are required to store.
In binary, log n
number.
bits are required to store that. Right? So log n is automatically coming in. So we cannot, so space is log n is nothing much we can do about it. Okay. Without extra log n space, nothing else can be done. Now, I am not proving you a lower bound here, but I'm just telling you that all the algorithms require log n, and you can think about whether you can prove a lower bound of log n also in this space complexity. I will not do it in this code.
But the constants in those cases were all 1, right?
Which constants?
In case of the log n space, the constants were not big like 26, they were all 1.
Yeah, that is true. That is true. The constants were not like 26, but they were 1 or 2 or something like that. But again, from the point of view of asymptotics, the log n is more important than the constant. Okay, because this n that we are talking about in the real life can be millions and billions of them. Okay, you are right. So yeah, in practical things, whether such a thing should be used or not, that's all those things will come in the picture later on. Because the constants can become 20, can become large. But at least in asymptotically, you can see that we have moved from order n log n to order n. Now, this is what is known as counting sort. So using counting sort, therefore, you can count them basically. Okay. Now there is something else. So, okay, now can you just now, so are you guys all comfortable with this counting sort? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
So another way of viewing this counting sort is, in some sense, what we are doing is that we had this whole string, right? We had this whole string, and we kind of created some buckets for A, B, C, D, and so on. And as soon as we saw A, we kind of dropped a bucket here. As soon as seeing it A, I dropped a bucket here. Sorry, this is, as soon as I say A, I begin put it here. Or at here, each of them I'm storing up number, say NA, which is getting incremented as soon as I see a A. As soon as I see a B, I am putting the NB is getting incremented. So in some sense, I'm just putting them in various buckets you can think of. Okay. Now, using this kind of an argument, can you think of sorting words? So if I tell you that the input are words, okay, the English words of length 10, what can you do? Or maybe let's not draw 10, of length a particular value k. English words of length k. Okay, so all of them are English words of k length English words, and I want to sort them. How would you sort them in a lexicographic order?
We can keep a 26 by k matrix where
26 by
each row-
k matrix.
Or
Right.
essentially a 26 into multiplied by k buckets, we can put them.
yeah, same thing.
Yeah.
Yeah, but 26 into k bucket is a lot, because say again, k is not a constant, right?
Sir, we can first sort them by their first letters. Those which like are in a draw position or have the same letter, then we can do the same counting sort for the second letter and so on. This would reduce the number of
So
letters.
first thing is that you make a bucket. How many buckets? Again, A to Z. And all the words that starts with A, so A star goes here. B star goes here. Similarly, star goes here. So I have split the whole input into 26 buckets. I have basically bucketed them. Now, what do I have to do? Do I have to sort them out? No, I have to sort only this one of them out, right? I have to sort this one out. It's almost something similar to what was being done in the case of quick sort kind of stuff like that. We are split up into, it's a kind of a recursive thing, but since here we know that there's a constant number of them, we are splitting up into this whole thing, right? Now, how much time does it take? So the first round, how much time does it take? First round, how much time does it take, do you think? First round is
26 and order n.
order n, right? Second one, how much time does it take? The second one, so let's say NA is the number of elements that has gone inside here in this bucket.
Sir,
So I
order
would take
max
order.
of NA, NB, and so on.
Okay, just 1 second. Yeah, your max of NA. You will order NA to sort them. Set. You will take order NB to sort this. You will take order NZ to sort this. So in the sort meaning the next step sorting, right? Which basically means you sort according to the the second bit of the string, second letter. So it is order of NA plus order of NB plus order of N, which is order of summation of NA plus NB plus NZ. What is this? What is NA plus NB plus
Order
NZ?
N.
This is N, right? So second round is also order N. The first one is order N, second is also order N, and you can prove that you can go down anytime. Every round will take order N, and you will do it for each round, meaning each index. So first we will do for the first index, then for the second index, then for the third index, for all the k indices. So the total time complexity will become order N times k. Now this is almost same as what you guys were saying about using this order nk sized square or buckets, nk buckets, and splitting it up. You are completely right. Okay, no, it will not be order nk buckets, because how many buckets, if you had just used buckets kind of stuff, how many buckets you would had to use?
Order of k buckets, essentially 26 k, but
Here we are using
Wait.
order of k buckets.
here we are using k buckets exactly. But in
Uh,
that proposal also it would be order of k buckets as well.
no, which proposal?
The matrix or the
Okay, so what was
initially-
the idea about the matrix?
No,
Can you
that
just
will
repeat
be-
again?
No, order NK buckets, not K.
Why nk
Why?
buckets? Can you-
Because we are initially introducing 26 k buckets, and then we are storing all the n in either of them. So it would essentially require 26 k buckets only. That
no,
is
why
the order of
26k? Can you say? Can you repeat once
Because
again?
we are essentially so the first one's first position k and a out of 26, b out of 26, these are stored in k buckets, and then for each subsequent position we would require 26 buckets. If all are order length k, all the words, then there are 26 many k many
Didn't it
26
be
buckets
like
required.
this? How many possible words are there?
Okay, yes.
26 to the K.
Yes,
That's not
yes,
very good. That's exponential, right?
Yes, yes.
So what you are saying is an exponential thing. That is how it will take if you had used just counting, but a clever bit of a mixture of counting and this kind of bucketing technique will help you to get down to order nk. So this is what is known as the radix sort. Now, is order nk better than order n log n? That depends upon what the value of k is, right? And what the value of n is. So if n is kind of much bigger than 2 to the power k, then this nk is better than n log n, else it is order n log n. Now, so this problem, this radix sort, how I have explained it is using the counting sort. Now, I know there are people who are interested in doing some coding, and so this is the question that I will be giving you as an assignment: is can you implement this radix sort in your using Python or C or something? I know that this code is available online, so that's not a hard job. But you, by doing so, you will understand how to use, how to basically keep track of, yeah, I mean, how to do this bucketing thing and all. So this bucketing thing, while we are explaining it in using theoretically what is going on, but exactly how you do this bucketing thing is not. You need to think a little bit more on that. So this problem of implementing radix sort so this is an assignment question. Okay. So any other questions that are there for this for sorting kind of stuff? Okay. You don't have any doubts, any questions? Okay, good. So let me tell you one more interesting thing that is something that we use a lot and for which we need another kind of sorting kind of an argument. So till now we have used only sets which have a proper ordering, meaning if I give you 2 points, say A and B, you can check whether A is less than B or A is bigger than B and so on, right? Or whether A is equal to B. These are the 3 options that were there. Even if it was guaranteed that A and B are coming from some special structure like a integer or a small integer or a small word and so on and so forth, you still had this special ability. So this is what we call as total order. Total order meaning that between any 2 points, I can either of these 3 statements is true. But many times in real life, what we have is not total order. For example, say you are in a industry, right? And in an industry, huge many number of people are working on various things. Maybe somebody is designing an algorithm, somebody is implementing the first part of the algorithm, someone is implementing the second part of the algorithm, somebody is talking to the clients, somebody is trying to find out data to do the implementation, for somebody is testing out the previous software, so on and so forth, right? But then there are certain ordering, like, okay, if you have to do implementation, before that the program should be done. Okay, maybe program 1 and first part and second part of the program can work parallelly. It doesn't matter which gets over first, but you should do the designing of the algorithm beforehand. In a production house, say, you have something similar to that, right? Say there are things like so maybe there's a, you have to solve, say, A, B, C, D, E, F. You have 6 things that you have to do, but the idea is that A must be done before B, B must be done before E, F must be done before C, also A must be done before D, and also E must be done before sorry, also D must be done before C, something like this. In this situation, how do you order this set of jobs? If there is someone, how can you say, okay, I want to first see this job is done, then this job, then this job, then this job, and so on. Is this problem clear?
you're saying partial, when partial order exists, how do we
Yes, so
sort?
this is the partial order. We do have a partial order, not a total order. Okay, I have a partial ordering, and in which case we have to find out a ordering. Now, for example, here one particular ordering can be, okay, first solve do F, then you do A, then you do D, then you do C, then you do B, and then you do E. This can be one ordering. Note that this ordering is a valid ordering because none of the criteria are violated. There can be other orderings also. For example, I can do first A, then A, B, D, E, then D, then C. This can be a ordering. Or I can do A, B, F, E, D, C. This is also an ordering. So you see that there can be multiple, it's not a unique ordering that exists. But certain orderings are not allowed, right? For example, D cannot be done after C, or B cannot be happening before A. So how do you find this kind of an ordering? An ordering that satisfies this partial order, this partial. Yeah.
So we can choose a particular node that is having no in degree, and then we can remove the age from that node, and we can repeat those process. Like we can repeatedly choose the node that are not having in degree in our repeated process, and then remove the
Okay,
edges.
good. So already you have made a one jump, major jump. First of all, you guys are talking about nodes and non-nodes and so on, right? So we are basically now moving, or once we have such a problem, the most natural thing to do is something that you can see possibly from the picture here.
Directed graph.
Formulate it as a graph. Exactly. In this case, a directed graph. Okay. So this problem basically says that, so the input, therefore, I can think of as a directed graph. G. What is an output? Output is an
Sir,
ordering.
Acyclic, right? Acyclic, directed acyclic.
Yeah, I will come to that. Yeah, very good. Output is V1 to Vn such that what? So there doesn't exist a edge between Vi R and to Vi S when R is less than S. Right, or the opposite, whichever you want to talk about, or the opposite, R is bigger than S. Maybe R is bigger than S. Right. So there is no backward edges in some sense. So backward edges like this are not there, only forward edges. Okay. First of all, question is that can we always guarantee such a thing's output exist? And the first thing that your friend kind of told is that in this graph, say, what happens if I had something like let me see. Yeah, an age like this. A has to be done before B, B has to be done before E, E has to be done before A.
It will result in a deadlock.
Right. So this is not possible, right? Is it not possible? Can you say in the world of graphs what's happening here?
There is a cycle.
There exists a directed cycle, right? So first of all, if there is a directed cycle, we are already doomed. So we can very well assume that this graph G is doesn't have any directed cycle or acyclic. Okay, good. So I start with a graph that is acyclic, and I want to output an ordering like this. Now, question: does there always exist such an ordering?
Yes, sir. Such a graph would always have a source node, and that is all we need. And removing anything that keeps it directed and acyclic, so that preserves. So basically, the algorithm that was mentioned before will always work.
Okay, yeah. So good. So I think let's rest of your friends also think about it. Okay, and we will be answering this particular algorithm. Okay, so next question is that design an efficient algorithm. Your friend has given already an algorithm, and the next thing is that okay, I mean, how efficient is that? So this is where we would like to take a small detour and go into this world of graph algorithms. Okay. So did we discuss graph algorithms at all in this course till now?
No, sir.
No. So was graph algorithms discussed in your previous discrete math course?
Not algorithms, but this was proposed as a problem. Topological sorting was discussed indirectly.
Topological sorting was discussed. Okay. Okay.
So it's not discussed. It was posed as an
Indirectly.
assignment problem.
Yeah, the whole argument of proving the existence and all that was proposed, not the algorithm.
Not the algorithm. Okay. 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 So okay. So let's take a small detour and go into the world of graph algorithms. Okay. So we will be in fact revisiting this particular problem sometime in maybe next week, the next class, but we will be sticking to the concept of graph algorithms for some time. Now, so okay, so why do we study graph algorithms? Okay, of course, it comes down to why do we study graphs at all? We study graphs because graphs helps us to model various other problems, right? Various other real life problems or other problems can be modeled using graphs. Particularly if the problem is related to binary relations, then graphs are a very natural way of representing. And therefore, so graphs are a very generic object on which if we are able to have a collection of algorithms, then we can, as and when we need, we can reduce. Now this word reduce I'm using it vaguely right now. We will do it later on more formally. But we can use some of the standard graph algorithms tools to solve other real life problems as and when required. So this is almost exactly why sorting was so useful. We had to study sorting as a introduction to the world of algorithms, as well as It's a very basic problem that we have. Graph algorithms is also one of them. So what is a graph algorithm? So the first thing is that input, this is a graph, and the output is something about say does the graph or something about the graph. Okay, output depends upon the problem, of course. Okay, some question, some answer to some question about the graph. Some question about the input. So is this clear? Is it clear? Okay, so if it is clear, let me ask a few questions then. Samipa Samanto, are you there?
Yes, sir.
Yeah. So have you written some programs? So you are used to writing programs?
Yeah.
So have you written programs about graphs?
About graphs, I don't remember right now. I guess no.
Okay. So if you see such a thing being written, is there anything that comes to your mind? Some question, some doubt?
I mean, how do you input a graph?
How do you what?
Input a graph?
How do you input a graph? Very good. So this is a most important question. How do you input a graph? Now, was this particular topic discussed in your discrete math course?
No, sir. No.
No, sir.
No. So how will you represent a graph? Let me ask you guys. So you have seen graphs
Adjacency
as
list.
adjacency list. Okay. Anything else? Okay. What is the adjacency list? What's that?
Adjacency list is basically represents the edges between the two vertices. That is that is suppose edge 1 to is connected to 2. So basically for the adjacency list should be something like 1, and there should be a list with that is connected to 1 that contains 2, something like that.
So we
Okay. So
can
represent
use
each of the node.
one by one.
Yeah, we can represent each of the node of the graph or the vertex of the graph as a linked list node. And if the graph is having some edges, then we can append the edges as the successor of the linked list node. And we can follow up with this.
So that is for everything. So we can use a 2D array, and if we are using directed graphs and weighted graphs, we can just store the weights accordingly. Like if the x-axis variables can be the source and y-axis variables can be the destination of the nodes, and then we can store the weights of the directed graph accordingly and have a representation of graphs.
Okay. So all three of you told basically a similar thing. So I got yet another answer in the chat. Binit Jha is saying the simple graphs are as 1D array. Okay, why is it 1D array? Okay, so I don't see that how is it 1D array? But basically, what all three of you kind of told is that you first have say an array with numbers 1, 2, 3. So basically, these are basically numbers corresponds to the the various vertices, the vertices v1, v2, v3 till vn. Okay, so a graph has a set of nodes. This is a set of nodes. Doesn't matter whether this is ordered or not, doesn't matter. So there's no ordering of nodes. Is there any ordering of the nodes? Of course not. So these are just some arbitrarily ordered ordering of the nodes. That's it. Okay. But now I also have to write the dependencies, right? Meaning the edges. So edges is written by every vertex will have a adjacent, will have a link to another array. What will that array be? That array will say that whether this node, what are the neighbors of this vertex, say maybe v3, v6, v2, and v10. v2 will have its another array, say v1, v3, v8. v3 will also have its another array, v1, v9, v2, and v11, something like that. Now one of you kind of talked about linked list. Now using a linked list here is a problem, because the linked lists are not that easy to move around, right? It's, you have to do it in a linear fashion. It is not a random access memory. But here I have giving you an array. There is no need of ordering them. There's no question of ordering here. Okay, and there's no question of ordering here either. These are any sum or some way. So if I want to add a particular vertex, I can add a vertex. If I know, why don't you add another neighbor? Okay, say v50, I added here. No big deal, right? Now, of course, I mean, this numbering is important. Why? Because this numbering are what is being written here. Correct. So this v10 is basically says that there is an edge between the node at the first one to the node at the v10 one. Okay. So this is what is known as an adjacency list. So usually at the end, you can, I mean, these arrays are kind of variable. So variable length. So what is the length of the array that is connected or hanging from the v1? What is the length of the array?
6.
Degree of V1.
It's the degree of v1, right? Similarly here, degree of v2, degree of v3, and so on. So what is the size of this adjacency list?
Two into the number of edges of the sum of degrees.
Ah, very good. So the size of the adjacency list is summation of the di plus, of course, there is the outside one, which is n, right? Plus n. But 2 of summation of di, degrees of the ith vertex. So this is equals to din. This is equals to, you have already seen that this is 2 times the number of edges. So 2 times the number of edges plus m. So in some sense, this is equals to what we call as order E plus V. So this is basically the most concise way of representing a graph. Is this fine? Okay. So if it is fine, I mean, this is not a unique way of writing a graph. I will talk about more other ways, okay? But this is one way. Okay. So let me see. Pradeep Das, are you there? Pradeep Das? Yeah. So did you follow this adjacency list model?
Yes, sir.
So if I give you two nodes, two nodes, say Vi and Vj, can you check whether Vi and Vj there is an edge between them or not, and how much time will it take?
Yes, sir. We find in adjacency list corresponding Vi and then the list corresponding Vi. If we find Vj, then Vi and Vj is adjacent.
But how will I find whether Vj is adjacent to Vi? How will you find it in the list? And what is the time complexity?
Time complexity order n square.
Why order n square?
Because first we start in first list.
Okay, so Vi is list.
Yes, then corresponding to Vi we start the list where Vj is there or not.
Right. So how much time will it take?
In worst case, order n square.
Order n square. Why are you getting order n square? I'm not getting it. Can you just tell me?
Order n.
Okay, why order n? Like, give me some explanation. You did not give me an explanation for order n square either, and neither did you give me an explanation for order n. Don't worry, don't be afraid. Just tell me. I mean, it will help me also to understand what you have understood and what you not understood.
First we start Vi in the red list first. This takes
Yes,
order n.
I am searching for. Why is it order n? Why is it order n? Can you just tell me? So I have hit here. I am looking at this list and looking whether Vj is there or not.
The order login first. Red list.
Okay, Pradeep, you are giving me different orders. Can you explain me why? What are you thinking? Why are you? Why is it order n? Why is it order log n? What is it?
Binary search.
Okay, so you want to do
In
binary
list.
search in this list, right?
Yes, sir.
Okay, if you can do binary search in this list, when you can type, then find whether Vj is there or not in order log n, right?
Yes, sir.
Okay, good.
Yes, sir.
But problem is that this list is not sorted. So how will you do binary search there? No, forget binary search. What happens if you do a very brute force search? How much time will it take? Pradeep, are you confused or something, or you told order n? Why did you tell order n? Let me tell you, order n was the right answer. Okay, Pradeep has disappeared. Huh?
In element. Then we start corresponding Vj in m element. Oh, order m
So
plus
in the
n.
worst case, this worst case, this will order n plus n. order n plus n. Okay. Okay. So in the worst case, the length of the adjacent, the neighborhood list of vi is n or n minus 1, whatever you want to call it, n minus 1. So it might be that you have to go through the whole list, because see, these lists are not sorted. So you might have to go through the whole list to check whether Vj is there or not. So to check if, say, I comma j is in the edge set or not, order n steps are needed in the worst case. Of course, I might get it in the best first search only. Note that since I am assuming that this is actually a array, so I can jump to the ith part or jth part in one step. So that's not a problem. But this array, they are not sorted. Okay. Now, if somehow I kind of assume, if, now this is a big if, okay, if the neighborhood lists are sorted, then ordered log n is required. To check if ij is in the edge. But once you say this, so this becomes a different data structure to some level, where you are insisting that these arrays are sorted. You can do that, not a problem as such. But then when constructing the graph, or when you add an edge and remove an edge, you might have to work on that much amount of hard work. Okay. So, okay, good.
Sir, you are saying log in respect to considering the graph as a complete graph, right? Because otherwise it should not be n. It will be much less than n.
It can be log. I mean, again, it's not a complete graph. I mean, it's a log degree you can think of, right? That's what.
No, I'm talking about like if a node is having n number of its degrees, then only it can be a complete graph.
Exactly. But we don't know. In the worst case, it can have n number of friends, right?
Yeah, that means it should be a complete graph to achieve log n.
No. A particular node can have degree n.
Log n to search in the first array and log n to search in the second array. That's what
right. That is 2 log n. That's true. That's why I'm assuming it to be ordered log n.
Right. But
no, but I think what your friend is saying, that this log n will be required only when the this array is of length n. Now that is true. That is the worst case. But you might have a graph might not be complete, might be far from complete. It can be very sparse, but one particular node can have degree almost n. What's the problem with that?
We have a complete subgraph of n minus 1. Yeah.
Or just one node, right? A graph something like this.
Yeah, one node can have n degree, another can have sparse degree.
Yes, and then you have to spend. I mean, if I want to check whether a particular I is neighbor of this or not, then I have to spend that much time, right?
Sir, but in one case, if I is before j, its neighborhood array will only have one element.
Sorry. Can you repeat once again? What do you say?
Here you are assuming that I will come after j. The one with higher degree will come before the one with lower degree. In other situation, you will have a sub array or the neighborhood array of size just 1 in the graph that you just draw.
That is true, but again, you can have graphs when both 2 degrees, 2 degree can have almost almost full nodes.
Right. True.
Okay, so this is not saying anything about the total graph. It's a very local thing that is being told. That it's yes, it is. I mean, you're right. So these things will not be ordered n, but ordered di plus order dj kind of stuff. that order di plus order dj can be order n. Similarly, this one also log of di, log of dj. Okay. So any questions about this? So this is actually a very important, where is it called? Yeah, a very important way of inputting a graph. So this graph, okay, would be a, this is, I mean, the most precise, the most concise way of giving a graph. But problem
Sir.
is that the, yeah.
Yes, so I have two questions regarding
Yes.
this. First is that the search operation overall would anyways take order log n, because searching in the list of vertices would be log n, right? Is that correct?
I mean, list of vertices will take log n. No, I don't
So we
understand
have to
that.
find vi or vj in the first list of the vertices.
Here,
Yeah, yes.
no, I'm assuming that you know. I mean, you know that. So
Okay.
the 10th vertex is in 10th place, kind of stuff.
But
like that.
suppose if we are analyzing the entire operation formally, then do we need to consider the list of vertices? Do we?
No, not necessarily.
Okay,
So
that
see,
can be
this,
accessed this way.
because these are names in some sense. We know we have a table to say that where the names are, right?
Okay, okay. So that can be.
So I'm
directly
asking.
accessed, yeah.
Okay.
And
I mean,
second thing
basically, we
is,
assume that there is an ordering here, and that ordering is something that you can fix, and that's it.
okay, okay, okay,
So it's a, I mean, not an important ordering. It's an ordering that's there.
okay. And the second thing for the DIDJ argument that I think Khalid was giving, that would only be like we can find the like the vertex with lower degree before we find the vertex with higher
Yes,
degree.
you can do that, but that will just
That would only be valid for undirected graphs, right? Because for directed graphs, the adjacency might not be represented in both VI and VI.
yes. Oh, very good. That's the one very important point that you made. So what is the difference between a directed graph and an undirected graph here? Can you tell me? Can you guys? So in an indirected graph,
Sir, I had a question.
yeah, go ahead.
How are you keeping track of? I thought that this is your general representation of a graph. Are you going to use the same thing for
It's a general
directed graphs as
representation.
well?
Yes,
I see. Okay. Okay.
I will do the same thing for directed graph as well. Okay, this is a general representation of a graph. Okay, so I can call that a graph is undirected if Vi is in Vj implies Vj is in Vi. If you can guarantee, if the input has that extra guarantee that Vi is in Vj's array, implies Vj is in Vi's array, then we can say that the graph is undirected. Right. Also, you have already seen things like weights, right? Weights on edges. You have seen them in your discrete math course, right? Graphs
Yes.
with weights. How will you put the weights? Where will you put the weights?
So along with the vertices we are storing in the adjacency list, we can just define a data structure. I
Exactly.
suppose.
Yeah, you can put a data structure and put a weight over there. V13, this is V16, and so on. So you can put weights on nodes by putting weights here. V1, W1, W2, and so on. So this data structure is a very generic data structure for storing any kind of graphs. Directed, undirected, weighted, unweighted, everything. Okay. But the problem is that even for such a simple question, we have to spend this much time. And this is a bit of a pain, right? Now, is there some other way of representing a graph which will help my this kind of questions to become simple or easy?
An adjacency matrix will suffice because we can get to the ith and jth index of that.
Right. So, yes. So, what is an adjacency matrix? So, adjacency matrix is a matrix which has the rows and columns are labeled in the same way order. So, V1 to Vn and V1 to V. Usually the diagonal is all put either 1 or either all 0. It doesn't matter what you put. The diagonal is all 1 or all 0 or something else also you can put. It sometimes you put some other numbers also. And at the Vi and Vj level, okay, you put 1 or 0. So if this algorithm, if this is called A, then A of ij equals to 1 if I comma j is in the set and 0 otherwise. So you see that by doing so, I can now represent the whole graph in this order, in this way also. Now, okay, you can say that, okay, is this general enough? Of course, it's general enough. Okay, what about the weights? If you want to represent weighted graphs, then you
Just
can.
08 instead of 110.
Yeah.
This is, you can put this weight here, right? Or if you want to store, this is, note that if when is it undirected? So if Aij equals to
Proper
Ajai,
triangle. Yeah.
or means that it is symmetric, right? Across symmetric around this on this side. For all ij, then it is undirected. So this is also another, yeah. Go ahead.
Yes, so just one query is this would suffice for simple graphs in some sense, but if there are multiple edges or loops, what do we do? Like, can that be
That
dealt
also
with in
can be done. That can also be done by putting these numbers. By putting numbers here,
Okay, okay.
right? Putting
So
numbers
when you
there.
say
Yeah.
So when you say
Right.
a graph, do you mean a simple graph? Do you mean like I'm facing troubles? Like what kind of graph you mean?
No, so in general, you can think of directed. I mean, so whatever I have been telling here, it is any of them. Okay, it can be directed, undirected. But yeah, for now, let's think of simple only. Multiple edges, I don't think we will be handling in this course. But simple directed graph, simple directed weighted graph.
Okay, sir.
Is what we are talking about. Say. Okay, but any kind of graph of that kind will be representable or can be representable using this data structure. Okay. Now, this data structure, what is the problem with this data structure? What is the cons? What's this bad
Its
part of the data
complexity is high, even if there are, if it's a sparse graph, you would still use a n squared size space.
Size is ordered n squared. This is can be much bigger than ordered n plus m, which was the case with adjacency metric list. So even if the graph is very sparse, very low, so m is very small compared to n squared, I have to put in this whole matrix. What is the positive with that? So this was the negatives, and what are the positive? Positive is, of
Search will
course,
be fast.
if I searching will be fast, right? Is I comma j in the edge? This takes order 1 step. right? All I have to do is go and look at the correct node point and output. Okay. Now, we will not be dealing with this particular thing too many times in our course, this particular representation, because most of the time we will be talking about adjacency list, but the adjacency matrix has some other important things. Okay. The thing is that this is a matrix. And as soon as you have matrix, what comes to your head? If you think of matrix, what comes to your head? All of you have done a course in linear algebra, right?
Yes.
So a matrix is an important part of linear algebra. So we can now ask about all of these nice properties of linear algebra. Like simple stuff. What is a square? What is a cube? What is a to the power k? Does that have some meaning or not? Okay. Matrix multiplication is a very important algorithm. We will be seeing that one later in the course. And once you have the matrix A, you can then ask about a square and all of them. What happens there? There are more interesting things. What are the eigenvalues of A? A is a matrix. So that means it has an eigenvalue. It's a symmetric matrix, a real eigenvalue. Symmetric matrix if it is if the graph is undirected. What does an eigenvalue mean? It cannot be just it's an arbitrary thing. There's no connection. So these are kind of things that I would like you guys to go and think about. Okay. You will be able to make some sense of these statements, and this will be a part of your assignments, which I want you guys to go and think. Matrix multiplication, we will be talking about this particular thing later on in the course. And eigenvalues, you cannot imagine the how much. So eigenvalues or the this is called the spectral properties. Is of A, okay, characterizes. I will write this statement and you kind of can understand it later on, or I can if you are interested, I can give you pointers to that. Characterizes how connected the graph G is. Okay, so maybe this is I should write AG. So here also I should write AG. So when I am talking about the graph G, then AG is the adjacency matrix of that. And this is something that's a very powerful thing. If you have heard of things about random walks and all of this stuff, they're all connected to this thing. So this particular, yeah.
Sir,
Can you
I
like
can
suggest
see.
some materials regarding this? How
Sure.
to upon this thing? Yeah.
Sure. So
I can
maybe
see.
the better option is that if you guys are interested, can you just come and meet me sometimes in my office?
Sir, is it okay if I meet you at 6:30 today? I have a class in HMU.
Today-
Afterwards, I can meet. 4 to 6.
Today
I have a class.
6:30. Just come over. If I am there, I will meet you. I might be there
Could you
today.
give a
but
specific time?
Okay, sir.
So usually I am there between say 11 o'clock to 5 o'clock every day. Okay. Maybe even a bit earlier, maybe a bit later. So that is usually a better time for me. Is this fine?
Okay, sir.
Yes, sir.
Yeah.
Sir, your first question is very similar to Markov chain, basically matrix of a Markov chain and then multiplying it gives us the total probability.
Think.
Here it will give you walk length, I guess.
Yes.
Or
You're
like
right.
total number of
Completely
walks
right.
of, yeah, look at
Completely
that.
right.
Okay.
Yeah.
Looks like that. Okay.
Yeah. So like I can give you a very, very specific question. Okay. What is the trace of a cube? And you'll be surprised what is it. And this will basically give you one of the very interesting way of calculating some object once you figure out what is going on there.
Can you be a bit louder? You're not audible clearly after the trace of it.
Am I not audible? Okay.
It was, but it was very low volume. So.
Okay. No, so I just that once you find out what does a cube represents and what is the trace of a cube, you will see that this is a very clever way of calculating a particular object about the graph. I'm being very vague here, so you go and figure out. I mean, the assignment will have something like that. So anyway, so to summarize, so this particular part is beyond this course. If you guys are interested, I'll be happy to meet you guys separately and give you separate reading materials. These are beyond this part of this course. Okay, matrix multiplication, we will see a little bit of that, and this is of course. But what is more important is that graphs, as I told you, I started with this thing, right? You have a input is a graph. From now on, you should always ask, whenever somebody says a graph algorithm, what does it mean by the input? Is the input given as an adjacency matrix or as an adjacency list? These two are different data structures. Both of them are very general, but have the very different characteristics. Adjacency list is the most concise way of representing a graph, but it is very concise. So it's kind of unwieldy to some level. Okay, so adjacency list is almost like giving a drawing of the graph. This is almost as good as you can get. Somebody has given you a drawing in a board, or how you have been used to dealing with graphs. Adjacency matrix, on the other way, is a bit more abstract way of giving a graph. You cannot immediately see from here what this graph drawing is. But because it has this nice matrix representation, it has different advantages of doing algorithms. It has a much bigger size, so you have a lot more redundancy in some sense is there. Okay. Most of the time, this adjacency matrix concept is used a lot in, say, machine learning and all of these things, where you use various linear algebraic techniques, linear algebraic algorithms for sparse matrices and all to solve this kind of stuff. Okay, so this is where we stand today. We have a graph algorithm. We are going into graph algorithm, and we now have understanding of what a graph is, how a graph is given. Okay, so in the next class, we will be going into proper graph algorithms. And we will start with graph algorithms. So just before I finish today, in your discrete math course, was any particular graph? So no graph algorithms were done, right?
No, it did not go into the algorithmic aspect of graph.
So did you go into the DFS, depth first search, breadth first search, and all?
No, sir.
No. So we generally characterize properties, like even articulatory problem was discussed, but Nothing in the
Okay.
algorithmic aspects.
Okay, okay. Okay, very good. Good. So maybe before I leave, I just want to say this number of people have gone down even further. I want to just run the poll once again. Okay, just to see how many people are actually there. Can we just fill up? I want to see which. Okay. Okay, fine. So yeah. Sir, yeah. Are you saying something? Pradeep, I cannot hear you. Yeah.
Actually,
Yeah,
sir,
tell me,
I'm
tell me.
sir, I joined the class with Sir Pradeep for some internet issue. Sir.
Oh, your name is different. That's what you're saying, is it?
Yeah, sir. I am Pradeep. Together, joined this class.
Okay. But that's fine. I just wanted to know about. I'm not taking individual attendance or something. I'm just trying to see which group is coming and which group is not coming. That's it. Okay, sure. So I will see you again in next class.
Thank you, sir.